So the next part, suppose that 0 and R are the only ideals of R. Deduce that, well, I could have just said show that R is a field, but I helped you by unravelling the definition of a field. A field is a commutative ring in which every non-zero element has a multiplicative inverse. So I'm simply saying what you need to show in order to show that R is a field. So we need to show that any non-zero element has a multiplicative inverse, a b that you can multiply it by to get 1, the multiplicative identity. Okay, so I have this element A. How am I going to show that this B exists? Now, if I don't use somewhere the fact that 0 and R are the only ideals, then there must be something wrong. Now, the point here is not that 0 and R are ideals. 0 and R are always ideals in any commutative ring. The point is that they're the only ideals, and that's the fact that I must use. So we must get ideals into it somehow. And just thinking about that fact that we must somehow use ideals, then that shows the way. I mean, the natural thing to do then, what can we do with this element A to produce an ideal to which we might apply this fact? Well, we'd look at the ideal generated by that element. So the ideal of all multiples of that element. Now, I don't need to prove this is an ideal because that was proved in lectures. In general, you can assume anything that was proved in lectures. So I consider the ideal A. Now, as an ideal, and given that these are the only ideals, it must be one or other of these. But A is by assumption non-zero. So the ideal generated by A, which in particular contains A itself, is not the ideal that just contains 0 and nothing else. Certainly every ideal contains 0, but this contains something else as well, so it can't be the ideal containing only 0. So by assumption, it must be the whole ring. And now I look again and I consider that later parts of a question are likely to use earlier parts. And I've just deduced that a certain ideal is equal to the whole ring. Now, it wasn't that long ago that I did part 1, so surely an ideal equal to the whole ring should ring a bell, right? In part 1, we showed that an ideal is equal to the whole ring if and only if 1 is in the ideal. So, it requires hardly any thought at this point to say, okay, from this I can deduce that 1 is in this ideal. So I can sort of do this without even looking where I'm going. But now looking and seeing whether that's getting us towards what we want, well, let's see. Okay, there's a 1 there and there's a 1 there. Maybe this is it. Yes, because this is the set of all multiples of A. And what we've just discovered is that 1 belongs to that set of multiples. And that's exactly what we wanted, right? 1 to be some multiple of A. So that's it. So i.e. there exists a B in the ring such that 1 equals AB as required. Okay, now we now have to do the other direction, which is part 3. So conversely, suppose that R is a field then what we've got to show is that 0 and R are the only ideals of R. Now again, the point is not to show that 0 and R are ideals. 0 and R are always ideals. I mean, that's the bare minimum. We always have 0 and R as ideals in any commutative ring. The point is to show that they're the only ideals, that given any ideal, it must be this one or this one. Well, so let's give ourselves an ideal and try to prove that. So let I be any ideal of R. So we must show that I is either 0 or R. Right, now we must show that either I is 0 or I is the whole ring. Now we need to be careful, because although in the last part the ideal we used was a principal ideal, that is the set of multiples of a given element, we can't assume that this ideal is principal. We can't assume that there's an A such that this I is the set of multiples of A. Now we certainly want to use the fact that R is a field, that given any non-zero element A, so again, we've got to look at this logically. We must use that R is a field, and if I simply remind myself what the definition of a field is, definition of a field is a commutative ring in which any non-zero element is invertible. Now that non-zero is important, and that suggests considering the case that I is not 0 and trying to show that I is R. So suppose that I is not just 0 and nothing else. We must show that I is equal to R. Now the point about I being non-zero is then that we can select an element of I that's non-zero. So we may choose an element in I such that A is not 0. And immediately I should be thinking, well, these are the elements that have multiplicative inverses. So since R is a field, there exists B in R, I could call it A inverse if I liked, such that AB equals 1. Now A is in I, and I is an ideal. That implies that any multiple of A is in I. Which implies that 1 is in I. I mean, I should have already been thinking that this is what I'm aiming at, again because I equals R by part 1 is equivalent to 1 belonging to I. And that's what I've just shown, that 1 belongs to I, and therefore, by part 1, I is indeed equal to R. So any non-zero ideal must be the whole ring. In other words, the only ideals are 0 and the whole ring, given that R is a field.